Hello everyone, this is a continuation of the design optimization basics that we've been talking about in class in ME 130. I'd like to first ask you to go to MATLAB, launch it, and direct your path to bopt intro. We'll be going through a number of folders again today, and we're going to look at a number of applications in MATLAB. We're going to discuss a number of applications in MATLAB with the fminconf function, the optimization function that we deliver an objective function, inequality, equality, and side constraints. I want to look at the concept of finite different step sizes as well. What we're going to do is, so far we've been looking at explicit functions, mathematical functions that we can solve analytically on paper, and then look at functions that are defined by black boxes. We have no idea what these functions look like. They have no closed form solution. We can use them as black boxes. Then I want to incorporate a multi-star technique, which we talked about a little bit last time, but we're really going to define today. Before we get started, though, I really wanted to show you this picture of the step size, the finite different step size concept that we talked about before. I want to draw your attention to the curve itself. This is f of x, just one variable, and let's select a finite different step size that starts here and goes there. So the largest step size. If we were to take a gradient using these 2 points, then what would happen is that we wouldn't really capture the dominant slope between those 2 points. It's almost like you on a ski slope with a ski that's much longer than the bump that you're going over, this well that you're going over. Now, if we selected a finite different step size that's very small, what happens if the simulation that we're using is noisy? The step size is smaller than these fluctuations due to noise. What we have to do is somehow come up with a correct step size which both doesn't get caught inside these noisy cracks, and what we need to do is find a finite different step size that allows us to both not get caught inside these micro cracks, but to also capture the dominant trend inside these slopes. We're ready to get started now. Let's go into our folder, go back one to the parent directory, and I want to look at a function a. And this is something that we looked at briefly in our last lecture. We just looked at the domain. We just looked at a contour map of the function. What I want to do is, now that I'm in this directory, I'm going to close all the files and start again. Master opt, function file, cons file, plot history and plot my data we really don't need to open right now. The function file looks like this. It's a very long function, but it's stated explicitly. So what we can do is use our rules of calculus, find the Jacobian, find the Hessian, and use the constraint information and iteratively do this by hand. The constraint file is one that contains neither an inequality nor an equality constraint, but we do keep the history over here. The thing with this file is that you have to return a C vector and a CEQ vector even if they're empty. You just feed them these empty brackets. So let's go into our command window and type master opt and see what happens, just so that we get used to using these functions. Okay, I'll iconify all the histories right now and the figures, and look at what's happening with this iteration. It goes from 0 to 10 iterations. There are 35 different function calls. You just ran this 35 times, and we started a function value which is rather large compared to its end value. Started 228 and all the way at -22. We see the max constraint violation here, the line search step length, and this is where we see a 0.5. At these points here, it's having a little trouble, so it says, you know what, I want a little more information. Let me do that. Let me find some more points here. The directional derivatives are here. They're decreasing as we go. And finally, we look at the Hessian modified twice, the Hessian modified. So it's having a little difficulty over here, but it's correcting itself and saying, okay, this is my new model for this landscape. And first order optimality is get closer and closer to 0, right? First order. And then we see that the x-opt is 1.9629 and 3.0, which is what figure 5 tells us. You can do this by eye if you had the time to draw a contour graph, and a contour graph that had enough contour lines. And that was the problem we had last time when we looked at this. We were having trouble determining where the contour lines were and changing these increments and then trying to do that graphically. Now, I have a question for you. What if, I'm going to close all of these figures right now. I mean, you can look at them and see how the optimizer had some trouble at some points and then had to do a half step. But what I want to do right now is open up this master opt file and change my starting location. Instead of starting at 3, -3, how about I start at -3, -3. Let me save this file and run it. Do you think I would get the same answer? Well, in this case, we came up with basically the same answer as we did before. And I'm going to hide these history figures, and we see that it had a slightly easier job getting to that point with this optimization run. See, it only used 7 iterations instead of 10, 24 function calls instead of 35. The endpoint is highly sensitive to your start point. And in this case, our final point, the optimum that it delivered to us, was the same in both cases. There are many times when this is not the case, where your optimizer gets caught in local minima and not global minima. And what I want to do is take a look at that right now. Take a look at those cases right now. Let's go into B function B. I'm going to now clear the console. I'm going to open master opt, func file, and cons file. The constraint file, we see there are no inequality or equality constraints, same as always. The function file has some function here. I can't visualize what it is immediately. Let's go to the master opt file, and we start at a -4, -4, and we have our design space defined there. Here are our options. This looks exactly like any other master opt file we've seen so far. Let's type master opt. And here we see something very interesting. This is known as a banana function, just because of the way it looks. And it's a classic problem that design optimization engineers use to determine the effectiveness of their optimization algorithms in finding a global minimum. And what we have here is a starting point at -4,4. We get gradient information here, skip all the way to the other end of the design space, and have a difficult time backtracking and going back and forth. And that's why this is such a good problem in testing your algorithm's ability at finding a global minimum. Now, it obviously found a local minimum, but we have no idea. Now, remember something. If each one of these points took an hour to run, I clearly would never know that the endpoint that I arrived at here is a global minimum. These contours are here just to show what the optimizer is doing, but in real life, you would never have knowledge of this space. That's an important point to recognize, that you never know what this design space looks like. And now what I want to do is go back to the master opt file and change the starting point. Let's go to 4, -4. Run it again. And see, it had an even harder time. It started here, went all the way there, backtracked back and forth like this. And a lot of this has to do with how the step sizes were defined and how the convergence criteria were defined. If I put another 0 here, another 0 there, maybe another 0 there, this would change. Where it ended up and how long it took for it to get there would change. In addition, the step sizes, the min change and the max change, these are known as finite difference step sizes. If I change this size, it would have a different trajectory. The history would have a different path. So as an what we've learned is that as an optimizing engineer, you have to not only run your optimization from one starting point, you have to be smart about starting different optimization runs at a variety of initial designs, and then you screen the outputs. If all of them are the same, then you have a really high certainty that that's a global minimum. If you have many locations that your optimizer ends up in, sometimes that's not a bad thing, because optimization isn't really about finding just one solution. It's about understanding the design space better. And sometimes you might find local minima that are not necessarily global minima, but are in much more interesting design locations. And that's what that's one of the many things design optimization engineers look at and look for when they're running their studies. I want to close all of these files right now, and I want to go into C function C-con1. Open that up, open the master opt file up and the func file. And again, these look very similar to what you've seen before. The only difference is in the cons file. Here we have no equality constraints, but we have one inequality constraint. And so I want to see how the optimizer deals with that constraint. Let's go into master opt. Everything looks like it's ready to go. Let's type master opt and press enter. And here's something interesting. We have a starting location somewhere here. Let's look at that again. It's at 0.5, negative 0.5, 0.5, negative 0.5. So we started here, and then it skips all over the place, but somehow comes back to where it started. And I want to indicate something here. You see this loop right here? This loop is the constraint. And the way I define the constraint is that everything inside this loop, in this area here, is in the infeasible regime. I started my design infeasible, it skipped out, turned around, and came very close to that point here that I'm talking about. I want to look at the function itself, which is this bimodal looking function. We see that if there were no constraint, the global minimum would be somewhere here, where you have a contour of 1. At the other mode over here, you have a contour of 3. So this is a local minimum, and this is a global minimum. And because we started close and it found out all this information during its path, it decided to end up here right on the constraint itself. And remember, whenever it's right on the constraint, the solution is right on the constraint, that constraint is called an active constraint. What I want to do now is start from a different location. How about, instead of 0.5, negative 0.5, we went to 2 and 2. What would happen then? Let's save this file, run it. 2 and 2. Okay, we're on this side. We start over here. It skips around. It gains some information about this design space. It isn't having such an easy time, but it ends up at the same point we had before. Let's go back to master opt and do negative 2, 2. Run this, see what happens. Hey, it found the same one. Let's do negative 5, 1. just out of curiosity. Negative 0.51. Look what happened. Because of the information it gained from this side of the graph, and because it was so far away from the constraint, and because the derivatives were in its path the way that they were calculated, it ended up in this local minimum. So what do we know about this type of optimization algorithm? Well, it's very good at finding local minima. So what we have to do is run this many, many times. This is called a multi-start technique. And this is what we're going to incorporate in our optimization studies. I want to try something different now. Slightly different. Let's go into directory dfunction c con2. This function that we're looking at, the objective function, is exactly the same. But the constraint file is different. It has a constraint here that is different from the constraint in the previous problem. Let's run this master opt file and see what happens. In this case, the function, the objective function, is the same, but the feasible design space is constrained differently. You see almost like these hyperbola right here? Well, the feasible design space is defined as the space here that I'm pointing, feasible here, and feasible out there. So nothing in the middle here is feasible space. What do you think would happen if I started at 2, negative 0.5? Chances are it would end up right there. But we started over here. It was infeasible. During its path, it found derivatives. And this knowledge led it to this solution. It's not hard to imagine starting it at all these different locations and having some of the results ending up right in this location, this local minimum, some right on this line, and then some right here. And this is one of the problems, and a lot of times most of the exciting things happen right at the edges of the design spaces and how you're constraining them. If you relax these constraints a little bit, the solution would look very different. What happens if the solution looked very different, but the value of that solution was identical? This is another very big problem. So what I want to do now is look at the directory called ffinalfunc. And I'm going to clear my command window. And I'm going to open up master opt, as well as func file and cons file. You guys are experts at this right now. We see instantly from the cons file that we have neither equality nor inequality constraints, and we're writing down a summary history. I want to look at this function file, which is a function of a square root of some numbers, the inputs, and a sine of all that. Then the master opt file, which looks very similar to the ones we've seen before. We see that the initial point is x1 is 0 and x2 is 1.0. We also see that the options are defined very similarly to the way that they've been defined in the past. Remember that these numbers, I picked these because I knew something about the design space. I perform what's known as pre-optimality, where I familiarized myself with the design space by performing some parametric studies, just so I saw how sensitive the system was, how it responded to change in inputs. And that's a necessity before you start any type of optimization study. You have to get to know your system so that you can better define what these tolerances are and what the step sizes should be. So what I'm going to do now is, starting with this x1, x2 as defined, I don't even want to look at the design space. I'm just going to run it, master opt, and what we find is figure 6 that contains this well-shaped parabola-looking function. I don't even know what you want to call that. And what I want to do is zoom in on the start point and where it ended. I'm going to start rotating things around, and if you remember, we started at one of these locations here, which was around 1 and 0. So that point exists right here where my cursor is, very close to that hump. And you would imagine that, hey, maybe it wanted to go down here and fall inside that well. That's a local minimum. But what it ended up doing was going all the way across the design space and finding itself in one of these wells. You see this circle that goes all the way around? Well, that's an infinite number of local minima. And there's one local minimum up here. I wonder what happens if I start changing these inputs around, these inputs for the initial design space, the initial design x1. Let's start somewhere else. Let's start at 5 and -5. What do you think would happen? Let's run it, and here we are. We start at 5, -5, and it goes all the way across. 5, -5 goes all the way across the design space, then somehow finds its way down to this spot right here. Let's zoom in on that. Finds its way down on this spot right here. It's not, again, not very hard to imagine that if you ran this many times, you would get an entire circle, a locus of points of all these optima. And I'm assuming that we would find a couple that would fit right in the middle in that local minimum. But again, remember that we're using these functions as black boxes. We don't know this function explicitly. I only plotted this function on the graph along with the history and the location of what the optimizer is doing, just so I could make a point that if we don't know what this design space looks like, it's very difficult to analyze what the optimizer's results are unless you perform this multi-start technique. So what I want to do now is go to these histories, and if we look at these histories, we'll see that we start at very different locations for the variables, variable 1, variable 2. We start at very different locations, and we don't converge like we did earlier with those earlier problems. Same thing goes over here. Start at very different locations initially, but don't end up at the same one. And that, for me, is something very interesting when I'm trying to optimize something. When I look at the objective function, though, we start at different locations, but we do converge to the same final optimum. So the solution, the value of that optimum, it's identical, but the location is very different. Okay, something to keep in mind. And so I'm going to close all of these, and I'm going to go to the next function that I want to look at right now. And this function, we have to scroll back a little bit and go to copt-adv. That's copt-advanced. And we have two subdirectories. And I'm going to select aopt-study. In here we see a series of m files, collect opt, cons file, master file, and we don't have a function file, we have a hidden function. And this m file was written a number of years ago. It opens up an input file over here, myinputs.out. It provides the x1 and x2 that's in the argument list hidden function. The file is then closed, and we have a call to an executable in the current working folder called my function. That executable file was written and compiled in Fortran, so we have no idea what this function is. Then we load the myoutputs.out file, which is the output file that comes from my function. So let's summarize. You have an input file, my inputs, that we open, we write to it, and it's prepared for the function, the executable my function, to run. Once this function is done, it outputs my outputs.out. And then what we do is we open up that file, parse it, and deliver the value to the function here. We look at master opt, and nothing has changed over here when it comes to the options in x1 and x2, except for the fact that now what we're going to do is automatically vary our starting location. So I'm coming up with a grid here, and I'm going to come up with a series of starting locations throughout the design space. This is the multi-star technique. And then I've defined an all opt matrix where I'm going to keep all of my optimum values as I go through these multi-starts. So what's going to happen is, in this nested for loop, what I'm doing is I'm changing the initial x1 location incrementally, keeping the lower bounds and upper bounds the same. Then I'm running my xopt equals fminCon function as before. I have an M file, which I'm not going to go into right now. It's a collect opt. What that does is it just takes all of the optimum, the summary files and all that, collects them and puts them inside the all opt matrix that we talked about earlier. Once this is done, we could find out how the optimizer is progressing through the design space from all of these different initial points. So remember, this is the multi-star technique. We're starting at many different starting points and then looking at where it starts, where it ends for all of them. So let's do that right now. Let's run master opt, and remember the function is we're blind to the function. It's just going to run, and if you remember, the increments were 5 long, so we're running 25 optimizations right now. And of these 25 optimizations, look at this final solution. Let me tell you what these black crosses and what the red asterisks mean. Of these 25 optimization runs, we get 7 different final solutions. 1, 2, 3, 4, 5, 6, and then 7. And this is where they exist in both x, y, and z space. The z is the optimum value. The black plus signs that you see on the x1, x2 plane are just the projections down to the x1, x2 plane for all of these solutions. And when you look at this, you're thinking, wait a second, of these 25, and you know, I've done it for 125, I've done it for 1,000, they all end up down here to these 7 points. What is going on with this function? What does this function look like? And which truly is the optimum? All of these points have the exact same convergence. They supply the exact same convergence and termination criteria. The first derivative and second derivative. And so without this multi-star technique, we could have just had one, and incidentally, we could have just stopped here and never would have known anything about the rest of this space. How would we have done it with the graphical method? Well, let's go back one folder, and I want to go to plot func only. And I want to open up plot hidden.m. At the top of this file, I look at x1 inc. What I'm going to do is use this number to do what we would have done by hand, basically. This increment changes the increments on both my x1 and x2 axes, and then I run this function down here after I scroll through the indices. Hidden function is the function that I wrote that we looked at before. x1 is that vector that gets sent to it, and function is what comes out, and then we'll mesh it. So let's save this, and then what I want to do is run plot hidden, and what we get is this function. Okay, that was quick enough, but imagine if each one of these points took a day to run. That would take forever, and if you looked at this space, you would think, well, the minimum occurs near, I don't know, 0, 0, it looks like, right around this point. If I, by eye, if I approximated some type of regression or some type of fit, I would say I'm pretty confident that the minimum occurs here. But let's square the amount of time that we're that we're allowing the computations to happen, just double that, the number of increments there, run this again, and this is going to take a while, but every time I increase that, I get something new. I learn a new characteristic about my design space. Look at what's happening here. This is a very strange function that if I didn't sample in a more finer mesh, I wouldn't realize that hey, 0, 0 isn't the minimum graphically. It's actually a little bit off. It's negative 1.5 and 0, positive 1.5 and 0. And then you think to yourself, well, let me increase the mesh a little bit more to about 30 and see what happens. Run this again, and again it takes a lot longer for this to run, and many times you're better off just running the optimizer from many different starting points in order to gain information about the design space. And here we have a nice smooth curve, and we can get smoother than this, but after running 30 by 30, that's over 900 times, we have higher and higher certainty that these two locations down here are the global minima, and we see it's now obvious to us that we have all of these local minima that the optimizer got stuck in, and that's why we had those 7 points in the previous design optimization run. So using that information, what I want you to do is bring all of that information together, the step sizes and the convergence criteria, the termination criteria, multi-star technique. I want to take all of those concepts and put them together into a problem that is associated with our STEAM tables. And I want to go into STEAM opt, STEAM opt now. And you have two subfolders in here. I want to go to aprob82 unconstrained. And this directory is all about this very simple problem, the ideal ranking cycle, no superheat. At point 1, we're saturated vapor. From point 1, we expand through the turbine to an isentropic condition at P2. If we have an inefficiency in the turbine, we can find out what point 2 is. Same thing with the pump. We have two pressures, P1 and P2. We're pumping from P3 all the way up to P4. We can calculate all this if we're given pressure 1 and pressure 2. We also define the turbine and the pump efficiencies, and we have to define, this is the last degree of freedom that we have to define, is the net power for the system. And we can do this using our WTP files. It's a very simple problem, but what I want to do is use this problem in the context of the design optimization concepts we've developed now. And what I want to do is vary pressure 1 and pressure 2 and see what happens to the net thermal efficiency, the overall thermal efficiency of the cycle, and see how I could maximize that efficiency. And so now we're in folder aprob82 unconstrained. If we open up the master opt file, we get something that we're very familiar with. At the beginning, delete all the previous files from the previous optimization run. Inits is an M file that once we open inits, it contains some of the assumptions and the givens from the problem. The current power, the net power for the cycle, and the turbine and the pump efficiencies. Also the upper and lower bounds. I come up with ranges and things like that. And then we come up with these loops that allow us to do the multi-star technique. You'll see that the tolerances on the function, constraint, and x are much looser than they were before with the analytical problems we were trying to solve. And the step sizes are a little bigger. But once we do that, how about we just run this master opt file, and we can take a look at the problem file where we use the WTP tables, but we've done that a lot in class, so I'm just going to go with it over here. It's running many different starting points throughout the design space. And what I want to do is close figure 6. This is a top view of the design space. And I want to look at this figure 5, which is the thermal efficiency of the cycle with respect to pressures at the pressure at state 1 and pressure at state 2. And just by looking at the TS diagram, we know that if we increase the pressure at state 1 and decrease as much as possible the pressure at state 2, we increase our thermal efficiency. You just need to look at the area between those curves. And you also have to think about the average, the difference of the average temperature over which heat exchange is occurring. If you maximize that difference, if you maximize the ratio of the high temperature to the low temperature, then your efficiencies are going to go up. What I have on this graph is superimposed the starting point of each optimization in a black circle and the end point of each optimization. And that's the blue asterisk here. And what we find is that each and every one of these optimization runs converged to the same final location and value. I want to look at the histories, and you saw these popping up as it was running, and we see that the thermal efficiency started somewhere for each one of these cases and then converged ultimately after a different number of function calls to about the same thermal efficiency. If we look at the pressure at state 2, we start at many different locations, 4 different locations, and then we converge to this final pressure, the minimum pressure that we're allowing it. In this case, the side constraint becomes active, the lower bound. And in the case of the pressure at state 1, the high pressure at the boiler, everybody wants to increase to that maximum pressure. So this is almost like a sanity check. Yes, this optimizer is working well. It's finding the correct solution. We know from fundamental first principles that this is what the solution should be. Now I want to look at a case, similar problem, exact same problem actually, that has constraints. And we go to B problem A2 constrained. And if you remember, all we have to do to change the constraint is to go to the cons file. And that's all I have changed in this problem. I have gone to the C line where we have the inequality constraint, and I initialized it. C1 is defined as 280 minus Q in. Now remember what we called the inequality constraint, the form that it's in. What this is Q in is greater than or equal to 280, and C2 is 750 is greater than or equal to x1 over x2. Remember, that's the negative null form. We don't have any equality constraints. So these are just random constraints that I chose just so I can see a point. And I want to run master opt. What I'm going to do is close everything, all the figures before I continue. And then I'm going to type master opt and run this optimization. And this again is a multi-start technique. And this is very interesting because automatically I see that the pressure at state 2 doesn't want to go to the exact same place. I'm going to iconify figure 6 or close it, and then I'm going to look at this thermal efficiency plot. And I see that all of the starting points, each one of these optimization runs converged to a different optimum. This is interesting because if I rotate this around, I see a very interesting pattern. I see that there's a line, this curve right here, that everybody wants to stop on, except for this straggler over here. Everybody wants to end up along this line. And this again is a very interesting problem. We don't have a single solution. A number of these solutions satisfy the problem statement. So now it's the job of the designer to find out more about the system, more about constraints, and use this information as a learning process to better define the problem. If we go to the thermal efficiency, we see that the thermal efficiency is right along that same line. Everybody converges around that same line. And from the histories, obviously, we saw from the previous mesh plot that they're not going to end up at the same place. They start different, they end different. They start different for state 1 as well, and end differently. So at this point, I want to start developing the codes that we can use to optimize the problems in class from now on.